welcome back, Quadrature fans. My name is Marian Elena, and today we will review box operators again. And so here we go. This is for the equation y equals x to the n. And our basic setup is, here it is. There's your grid. We go always from 0. And we go, here's the x-axis, and here's some point alpha. And so if this is an x to the n, the parametric form of this point here is alpha and alpha to the n. This is the x value, and this is the y value. Okay, and this could be anywhere along this curve. Notice that we always start at 0 for the box as well as for this diagonal. There are two things that we're always going to be looking at. We're looking at the box and the diagonal, or area and tangent slope. The area underneath this curve we want, and the tangent slope here. So basically this point is alpha to the n. It could have been x and x to the n. For a simple curve like y equals x to the n, that would suffice. But when we go to more complicated curves like y to the m equals x to the n, then you really have to parameterize these things, and that's where the parametric becomes very useful. I'm trying to introduce you to that now slowly. And alpha, well, that's, okay, think of it as a simple variable, but we are moving toward polynumbers and, yeah, polynumbers. So a review of these box operators, and there are 4 of them. Basically, the box of x to the n, well, no matter where you are here, starting from 0, the box is this box. That's the BOX of x to the n equals x to the n times x, or alpha to the n times alpha equals alpha to the n plus 1, raises by 1 power. The the characteristic diagonal, this diagonal here, which always starts at 0, and it goes, to this point here. Well, that's, you could say it's x to the n divided by x, or alpha to the n divided by alpha. That equals alpha to the n minus 1. It decreases by 1 power. Okay. The integral of x to the n, that's the area here, right here, from 0 to x equals alpha, so this wedge. Well, that's the box of x to the n times k sub n, which we have found is 1 over n plus 1. Well, that's simply alpha to the n plus 1 over n plus 1. And this is known as Cavalieri's formula, okay? Cavalieri found that in the 1640s. So this is hundreds of years old, okay? The derivative d of x to the n, well, that's diag of x to the n times c sub n, which is n times, alpha to the n plus 1, or n times x to the n minus 1. We decreased by 1 power. Notice here we increased by 1 power. In the integral, in the derivative, we decreased by 1 power. And that's the nature of these box operators. And notice that in our world, everything is definite. That is, it starts always from 0 to some point alpha. And that applies for the box, as well as the diagonal, too. This diagonal, it ranges over, here's from 0, and here's alpha to the n. So this is a definite region. So there's this, I don't know if this makes sense, but In quadrature, there's this thing called definite derivative. Maybe, I don't know. Let me know what you think. This is a weird term. I've never heard of such a thing. In calculus, you never hear of such a thing. But, quadrature is a little different. Quadrature doesn't have a concept called indefinite integral. Everything is definite, starting at 0 to some defined region. Always 0. And so here's the deal. If we want to know the area of a curve y equals x to the n, and it goes from some point to some other point like this on the x-axis, which is non-zero, what are we going to do? We can't do this directly. What we have to do is break it up. We have to break it up and use properties of area, additivity, and dilation. And so that's exactly what we do. So if we want this wedge right here, the area, well, then we have to take the big wedge here, always start at 0, and here we go to 1 plus alpha, okay? And so we find out the area of that, and then we subtract out this little area. So we have, there's our box, and so here's our little area multiplied by k sub n. That gives us our little area here, the area of this little wedge. And we subtract that from the area of the big wedge, and that gives us the remaining area here. And the other way is to use translation, and basically you start out with y equals x to the n, and you say, well, okay, x equals 1 plus t, because here 0, 1, 1 plus alpha, minus 1, 0, and alpha on the t-axis. So it's been shifted, translated. And so now t starts at 0, and that's our rule in quadrature. We always have to start at 0. And so this wedge here is made up of a bunch of little functions. This would be constant, linear, quadratic, cubic, and so on, all the way up to x to the n. So using this translation, we basically come up with this translation equation of y equals 1 plus n alpha plus n minus 1 over 2 factorial alpha squared plus n minus 1 n minus 2 over 3 factorial alpha third, dot, 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 etc., all the way up to alpha to the n. That's binomial expansion. That comes from the translation equation. And then you use box operators from then on to do both slope and area. I've done that in previous video. You're welcome to watch that. But that's kind of one way. And let's look at box operators from Norman Wildberger's famous work. This is his famous math problem 10b, and there's the link to it on the YouTube. And so there's slide 8 and 9. There's Norman. And basically we're going to zoom in on slide 9 here. That's where everything is kind of interesting. So he's using this. This is your box, BOX, 1 plus c to the n plus 1. And multiplied by a sub n. So now he's dealing with area. This would be the integral. And then this, that's the little area. That's the box, BOX. And multiplied by a sub n, that's the integral of the little area. And so this is also called a dilation and additivity type relationship. You should watch his video. He's really good at that. And then he leverages that against the translation, those little functions that I've showed you. And again, a tip-off, you see c times a0 n c squared a1. So here's another, basically, here's box, and here's the integral when you multiply it by a1. Because this is the linear, this would be the constant term. This would apply to the linear term. The quadratic term is n choose 2. Now notice he's using slightly different notation. He's using n choose 2, but that's the same thing as my n minus 1, n minus 2 business that you saw earlier. It's identical. You should do some research on it, convince yourself that that is so. So indeed, these are all box operators, and these are all areas, the little functions from the translation, the t perspective, which always start at 0, remember that. And so he goes all the way up to, you know, c to the n plus 1, which should be canceled out. And yeah, so that's Norman. I'm Marian Elena, and before that was calculus, that was quadrature.